Teams shipped the wrong feature because they saw a metric rise after a release and assumed the change worked. The misconception is that a strong correlation means the feature caused the rise. Mathematically, they are turning a pattern of co-movement into a claim about what would happen under an intervention that isolates one variable and holds the environment fixed. Picture yourself in a review with a dashboard where a metric and a feature trend upward together, budget's already shifting, while an unmeasured seasonal tailwind is quietly pushing both. Correlation is about how variables move together, not about what makes what happen. It asks whether higher than usual values of one variable tend to line up with higher than usual values of another, or with lower than usual ones. It is a shape description of data, scaled so that it ignores units and focuses on alignment. Causation is a different question entirely. It asks what would happen to an outcome if you reached into the world and set a variable to a specific value, while keeping everything else the same. That last clause is not decoration. It is the whole difficulty. Consider a common headline that coffee drinkers have more heart disease. Early observational data made it look like coffee was dangerous, with about double the heart disease rate among coffee drinkers compared to people who avoided it. If you stop there, the practical advice is obvious and wrong. The missing piece was that smokers were much more likely to be heavy coffee drinkers, and smoking directly raises heart disease risk. Coffee and heart disease moved together because smoking was pushing both. That structure has a name, and it shows up everywhere. A confounder is a variable that influences both the thing you think might be the cause and the outcome you care about. In the coffee case, smoking increases coffee consumption and increases heart disease risk. When you compare smokers to smokers and non-smokers to non-smokers, the apparent coffee effect mostly disappears. The correlation you saw was real in the data, but it was tracing a pathway that was not coffee-making hearts fail. The most common beginner mistake is to read a big correlation and a tiny chance of randomness as proof of cause. That tiny chance of randomness only tells you the pattern is unlikely to be noise given the model you chose. It does not tell you the pattern is a causal effect. It does not protect you against confounders, reverse causation, or selection bias. Taking that shortcut costs you accurate decisions, and in fields like health or policy, it can cost lives. In business, it burns money and erodes trust in analysis. The mental model you need separates association from intervention. Association is a summary of how your sample behaves. Intervention is a statement about worlds you did not observe, where you change a variable and want to know the outcome. Those are different universes. If you are not clear about which one you are talking about, you will mix them without noticing. When people say correlation does not imply causation, this is what they mean. A pattern among measured cases does not tell you what would happen if you actively changed one input. There's a practical correction you can use before making any causal claim from data. Write the claim as a do statement in plain language, as in, if we make this quantity higher, the outcome will go up by this amount. Then ask whether time order is clear, whether there are variables that feed into both the input and the outcome, and whether your data set was filtered in a way that might create a false link. Build a short list of rival explanations that could produce the same correlation. Then try to rule them out with design choices, comparisons within similar groups, or by showing that the effect persists when you block the obvious backdoors. Randomized experiments work because they break the connection between pre-existing differences and the treatment. When you assign people or units to conditions by chance, the reasons that would normally make some choose treatment and others avoid it get scattered across groups. Now, on average, the treated and the untreated look the same in all the ways you did not measure. Under that design, a difference in outcomes can be interpreted as the effect of the treatment instead of the effect of who chose it. Randomization is not magic, but it makes the causal question match the data. Many times you cannot randomize, and you still need to decide. Then you design your comparisons to be as close to the intervention idea as possible. Compare like by matching on key predictors of both the input and the outcome. Adjust with models to remove the part of the association explained by known confounders. Split the data into strata where the confounder is nearly constant, and compare within each stratum. None of this guarantees a causal answer, but it reduces the room for a misleading one and forces you to state the remaining assumptions. Be on guard for reverse causation, where the arrow of influence runs the other way. People with worse health often take more medicine, so you will often see medicine use associated with worse health. That does not mean the medicine harms them. It means the illness is causing the treatment. Usage and outcome move together even if the treatment helps, because the treatment shows up when the problem is severe. Time order helps here, but even with time, feedback loops can produce strong associations in both directions. Selection bias is another trap that creates misleading correlations from the way you get your data. Imagine you analyze only loan applicants who are approved and then notice a negative link between income and default. You might conclude that higher income causes more default, which contradicts everything you know. What happened is that the approval rule filtered out most high-risk low-income applicants, leaving a skewed pool where the remaining low-income cases were unusually solid. The active conditioning on approval created a false relationship. This kind of bias hides in pipelines, product eligibility rules, and survival to the point of measurement. A classic warning sign that these structures are in play is when the association changes, or even flip sign, once you break the data into sensible subgroups. This is the pattern known as the paradox, where the pooled data misleads and the stratified data tells the truth. The fix is not to always slice the data thinner, but to slice it along variables that could be confounders, not along arbitrary categories. If a variable is a cause of both your input and your outcome, compare within its levels. If a variable is a consequence of your input and your outcome, avoid conditioning on it, because that can create a false pathway. Now, about the correlation coefficient itself, it is a summary that captures linear co-movement. That means it is blind to relationships that are strong but curved. It is also brittle when extreme points are present, because a single outlier case can dominate the calculation and swing the value in a way that misrepresents the main body of the data. A high correlation can come from a few points far out on a line, while most points are scattered. A low correlation can hide a stable curve relation that would be obvious if you saw the raw pattern of points. Falling in love with a single number invites a second beginner mistake. People try to beat the correlation into telling a story it cannot, like asserting cause or ruling out confounding by simply adjusting in a model and declaring victory. Adjustment is not a washing machine that removes all stains. If you leave out a key confounder, or if your adjustment inadvertently conditions on a downstream variable, the number you report can be further from the causal effect than the naive association. The cost is false precision and decisions that depend on the specific model rather than on the structure of the data and the question. If you need a workable way forward, start with design, not with models. Define the units, define the time window, and think through how the data landed in your table. Choose a comparison that makes it hard for a confounder to explain the result. Ask for pre-trends when you can, because a past pattern moving in the same direction weakens the story that your action caused a sudden change. Seek negative controls, variables that should not be affected by your action, to check for shared biases. These are habits that improve the quality of your conclusions before the first calculation. When you do model, use models to support a design, not to create a design after the fact. If you match or stratify, make the resulting comparisons transparent by reporting group differences before and after adjustment. If you regress, explain which variables you adjusted for and why each one blocks a confounding path rather than introduces a bias. Try alternate reasonable specifications to see if the claim is an artifact of one set of knobs. Do not hide behind a standard tool. Expose the assumptions you are relying on and show how the result changes when those assumptions move. Mechanisms help, but only when they connect to the data. A believable story of how something works strengthens a causal claim if the story suggests patterns you can test and you see those patterns. If the mechanism story never touches a measurement, it is decoration. Use mechanism thinking to predict which subgroups should show a stronger or weaker effect, which timing should match the claim, and what should not move if the cause is real. Then look for those signatures. Empty mechanism stories will collapse under this kind of pressure. The key shift here is to treat correlation as a clue and causation as a design problem. Association tells you where to look and what to ask, not what to believe about interventions. Causal claims live or die on whether your comparison mimics the world where you set a variable and hold the rest still. If you adopt that frame, you will stop confusing co-movement with influence and start building arguments that survive contact with data and alternatives. Next comes what a scatter plot reveals that a number never could, where you will see how shape, gaps, clusters, and outliers answer questions your summary cannot.